Why do field lines never cross and why do they explode out of sharp corners? So let's break down what electric fields look like and how they behave near conductors. So what are electric field lines, first of all? Instead of drawing a field vector at every single point, we draw lines that show the direction of the electric field and where the field is stronger or weaker. So stuff like this. And when your charge is negative, then the lines point toward. The electric field lines follow the direction of a force on a positive test charge. That's the rule. Here's some properties of these field lines. So the lines obviously show the direction of the electric field, but they also show strength. So how strong the field depends on how close the lines are together, the density of the lines. On positive charges, the line starts. On negative charges, that's where the line ends. And the number of lines is proportional to the size of the charge. For example, a positive 2 charge has twice as many lines as a positive 1 charge. The lines never cross. Each point has exactly one field direction. They'll never cross like that. Next, I'm going to go through a bunch of these fancy diagrams, which is probably what you came to this video for. This is a classic dipole. One positive charge, one negative, equal in magnitude. The field lines start at the positive and they curve smoothly toward the negative, and that's where they end, like we talked about. At the midpoint, the line spacing is less. It's very dense, meaning the field is strongest about the middle. Why do the lines curve? It's because at each point, the electric field is being pulled in 2 directions at once. Because it's got its normal electric field path, but it's also being pulled toward that negative charge. If I placed a tiny positive charge somewhere around this setup, it would follow the curved line like a little roller coaster, and it's going to get pushed along. So to sum up our first important diagram, a dipole is just 2 equal and opposite charges that are separated by distance. The field pattern is curved and symmetric. Here's the second diagram, which I'll quickly draw now. What's going on here? There's 2 positive charges this time. There's no field lines that are connecting them because they repel, right? Like charges repel. The lines radiate away from both. You can see they come out and then they get pushed away. They're getting pushed back like this. Now, if you place a positive test charge Q in between them, anywhere here, then it would instantly get squeezed outward and away. And here's something interesting. Right here in the middle, the field is weak and the forces here actually cancel. Why? Well, if you have this positive one at a certain distance and this positive one at a certain distance, the positive charge on the left will be pushing it to the right, just as much as the positive one on the right is pushing it to the left. It gets held here in equilibrium, so the forces cancel out. This point is called the null point. What's going on here? Now things have become lopsided. On the left, we've got a negative charge, and on the right, we have a positive charge with twice the strength. It's again opposite charges, so lines still flow from positive and end at negative. But here's the difference. Because there's twice the strength, twice as many field lines leave it compared to the amount entering the negative charge. This is not just visual decoration. The line count is proportional to the charge magnitude, so the field lines near this double charge are denser. The shape is curved like a dipole, but skewed toward the bigger charge. See, there's a certain amount of lines going into the negative charge, but there's a lot more coming out from the positive one. So line density, how close they are together, equals the field strength. More lines equals stronger field. That's how we visualize things. These are parallel plates. This plate is positive and this plate is negative. They are equal and opposite. The field lines go straight across. They're perfectly parallel and they're perfectly spaced. This means that every single point in between has the same field. So that means the same magnitude and the same direction. This is called a uniform electric field. So since it's a uniform electric field, that means E is constant. It's not just the value of E, it's the entire vector. So both the magnitude and the direction that stays constant everywhere. The field flows from the positive plate to the negative plate always. Same size, same direction, no matter where it's placed. Why does it start to bulge outward at the edge? This is called fringing. It happens because the field is no longer perfectly symmetrical here. And this happens because the edge of the metal can't hold the same distribution of charge as the center. But in physics problems, unless they say otherwise, we usually ignore edge effects and we treat the field as perfectly uniform. So to summarize before we move on, straight field lines means a uniform electric field. Curved lines means it's a dipole or an asymmetrical setup. Dense lines means strong. Sparse lines means weak. And it enters from positive, exits to the negative. No crossing ever. Never ever will field lines cross. What if we bring metal into the picture? What happens when you place charges near conductors? If you remember what a conductor is, it's something where the electrons inside can move around very freely. So it's easier to charge. Inside a conductor, let's say, it looks like this. Inside of it, if it's at rest, the electric field is 0. This is because the free electrons inside move until they cancel out all internal fields. Any field that's not 0 would cause motion. There would be a net motion inside. But in electrostatics, everything settles to E equals 0 when it's inside. Now, electrons spread out as far as they possibly can from each other. That's what they like to do. On a hollow conductor, that means charges move to the outer shell or the surface. If a positive charge is placed in the center, like this, all the negative charge gets attracted toward it, and all the positive one gets pushed to the outside. If you sit inside a metal box in a lightning storm, why are you safe? There's thousands of volts hitting the roof, but nothing happens inside. Why? Picture a hollow metal sphere sitting in the middle of some kind of uniform electric field, like a bowl that's floating in between two giant charge plates. You ask, what's the electric field inside the hollow region of that metal? The answer, 0. The electric field inside is always 0, no exceptions. Why? Let's break it down from principles. So first of all, conductors have free electrons. The electrons can move however they want. They're not locked in place like inside an insulator. But the moment an external electric field touches the metal, the field tries to push the electrons in one direction. So they all immediately start moving. But they don't just move, they rearrange to cancel this field and make the electric field 0. Because they shift across the outer surface of the metal, like we were talking about earlier. And in doing so, they create an opposing electric field of their own, which perfectly cancels the uniform electric field coming from outside. That induced field exactly cancels it, but only inside the metal. How about the hollow region? Once the charges settle, the metal has rearranged itself so perfectly that the field inside the hollow space is completely gone. There's no field. It's 0. There's no line sneaking in. There's no partial fields. It's not weak. It is nothing. This is called electrostatic shielding, which I think is a really cool name. The definition is when a conductor redistributes surface charges to cancel all electric fields inside of its hollow cavity, leaving E equals 0. Electronics are stored in metal enclosures to block external EM fields. So this works only in electrostatics. That's something you have to keep in mind, which means that the field is steady. If the field is changing fast, like in high frequency electromagnetic waves, the shielding still helps, but the math is a lot more complex. So to wrap up this video, field lines are not vectors. They are what we use to visualize and draw stuff coming out of charges.